Hello, my name is Adam from the University of Cambridge, and today I'm going to talk to you about my poster at the IMLB on vertically aligned nanocomposite thin films incorporating 3D architectures for solid-state battery applications. So, what is a vertically aligned nanocomposite? Well, you can think of these structures as being like chessboard structures, where the black squares correspond to one material and the white squares correspond to another. They're comprised of single crystal-like columns embedded in a matrix phase. They form by thermodynamic self-assembly, one of the few examples of solid-state thermodynamic self-assembly. And we typically grow them with PLD, but they can be grown with chemical vapor deposition methods. Why are they interesting? Well, they have very high interfacial surface areas, which makes them interesting for studying interfaces, as you will discover on my next slide. And they remain a very novel area for lithium-based systems, with only 2 papers currently published. So why might you want to study these materials? Well, firstly, you might use them as a model system to study battery interfaces. Why? Well, battery interfaces, solid-state interfaces are buried, and they're very small, which makes them incredibly difficult to probe. But Van's films offer a solution, really down to 2 reasons. The first being it's a substantially larger interfacial area due to being a 3D architecture. And this interface is also surface accessible, allowing techniques such as AFM to be used. Secondly, many of these Van systems have shown enhanced properties, particularly enhanced ionic conductivity due to hypercrystallinity. Also lowered a real surface resistance, which is important to getting a good performing battery. We can also play around with strain engineering to play around the physical properties of our material. And we can also stabilize challenging phases by using the matrix as a scaffold to support columns of a difficult phase to grow. And finally, why Van films are an example of a 3D battery architecture, a very hot topic in the field at the moment. This may allow us to get increased volumetric energy densities and energy storage capacities. But why is Van unique over other methods? Well, first of all, we have a usable geometry because our columns are perpendicular to our substrate. But Van is also a one-step process. We don't require etching. We can just grow our 3D architecture in one go. And we get nanometer scales, with the columns typically be on the order of 10 to 50 nanometers in diameter. So on to some results. In the top half of my poster, you'll find a segment on our recently published paper in APR Materials on this lithium lanthanum niobium titanium oxide electrolyte with titanium niobium doped titanium oxide anatase nanocolumns embedded in it. This is effectively an electrolyte anode fan system. From the TEM, we have really high crystallinity and clear phase separation between the 2 phases. The titanium oxide phase is clearly seen protruding the surface of a dense matrix film. From impedance, we observe a very high ionic conductivity, in fact, on the same order of magnitude of the best available LLTO films. This is significant because it is known that doping niobium into LLTO lowers the ionic conductivity of the phase. So we can so in our system, we can retain the high conductivity by compensating for the lowered conduction of the phase by increasing it with the Van structure. We probe the electronic conductivity with current sense AFM. What is quite nicely seen in this AFM image is that the regions of high current correlate with topography, and those in the context of our TM, those are the columns of the electronic conducting niobium doped titanium oxide. But the current remains quite low. And this is something that we learned and later correlated with this little thin film layer that grows underneath the column. This led us on to developing our second system, which you can find more out about on my poster. Finally, I would like to thank all the people who have helped me in my 4 years of my PhD, which is sadly coming to an end, and particularly also the funders who have supported me to do this research. I hope to see you in Sydney, and all the best.